Welcome to Unit 1, Section 5. All right, hopefully by the end of this lesson, you'll be able to perform operations with complex numbers. And there's a little cartoon there at the bottom. It's kind of cute. You may not get it now, but by the end of the lesson, you'll understand it. It is kind of funny. So hopefully you can enjoy it at the end. So take a minute and pause the video, and then we will get going from there, all right? All right, so I'm going to assume you pause the video to write this down, okay? So let's get moving. All right, I want you guys to think about this for a minute, all right? Remember, we already defined the number I, the imaginary number or the complex number I, as a square root -1. So, if you square both sides of that expression, that equation, right? You end up with I squared equals -1. Therefore, I to the first equals 1. So I squared equals -1, then I cubed equals -I. Can you find I to the 4th, I to the 5th, I to the 6th, I to the 7th, and I to the 8th? Do you see a pattern? Can you use that pattern to find I to the 19th? What about I to the 243rd power? Okay, I'd like to see you guys make an effort at this and really try it. I'm expecting to see this in your notes. Okay, and we'll go over it and we'll find out what you guys discovered in this exercise when you come back to class. All right. So I hope you paused this video and took a stab. All right, so we've been talking about complex numbers, we kind of a little bit yesterday, and I introduced you to the form. Complex numbers have the form A plus BI, where A is the real part, and B is called the imaginary part. And that's, again, because B goes with I. Now, does that mean that B itself is an imaginary number? No, that just means B times I is an imaginary number, okay? Can these things be represented graphically is what I'm asking you. And the answer to that question is yes. Yes, we can represent complex numbers graphically, and it's actually kind of important. We're just going to touch on it now so that I can introduce a couple ideas to you, and then it is going to be really important when we get to trig and some other stuff later on in the year, okay? But yes, we can represent these graphically, and this is how we do it. So what we have here is we have a complex plane. Like before in Algebra 1, you had an x and y plane. We call that the Cartesian coordinate system, right? Well, complex numbers are represented as with a real part and a complex part, and each axis corresponds to that. Each axis corresponds to the real part or the imaginary part, like x and y. So the complex axis is equivalent to the y-axis. The real axis is equivalent to the x-axis, all right? So let's plot that. Let's plot A plus BI. Here it is. That's my spot, A plus BI. That is how I would graph A plus BI. You just go over how many ever. It's like a coordinate. You can think of it as a way of writing a ordered pair, okay, or a coordinate in the Cartesian plane. Something I forgot, sorry, I got to throw this back in there, is that number z equals A plus BI. This is not something you're necessarily going to see a lot of, this z here, okay, but z means a complex number in math. It's a notation thing. So z means complex number. Complex number. And it means a number of the form A plus BI, all right? Just want to throw that in there really quick. Another thing you're going to see talked about occasionally is the absolute value or magnitude of a complex number. All right, and what that is this. It's the distance from the point to the origin. Check that out. It's the length of this segment right here. It's that length. It's that distance, all right? Well, how would you go about finding that distance? Let's think about it for a second. What if we dropped a perpendicular? Oh, let's do that again. Let's try that again. Oh, let's put our highlighter back. There we go. From A to there. All right, now, guess what that forms? That forms a right triangle whose legs are A and B. So that means my missing side, we call that C for a triangle, correct? And you should all know what? The Pythagorean theorem, right? And the Pythagorean theorem says A squared plus B squared equals C squared. So if I want to solve for C, we should all know this by now as well. You take the square root. You're going to take the square root of both sides. And when you take the square root, remember we kind of said when we're solving, it's always plus or minus. But in this case, it's going to be a little bit different. Because we're talking about a distance here. And a distance is always positive, right? We're talking about a measurement. And measurements are positive. You can't measure negative things. I mean, they talk about it in science a little bit, but we don't measure negative things. So C is going to be positive. And that's going to be the square root of A squared plus B squared, all right? So oftentimes, what you'll see is this, this is one way of seeing it. You'll see that this or this, or you'll see this. Wait, that's it. That's what we mean when we talk about magnitude generally, okay? Magnitude or the absolute value. That's why they say absolute value, because you see the two lines there. We talk about magnitude in vectors, but it's the same thing here. In math, we don't generally use the term absolute value this way. We talk about the magnitude, and the magnitude is the size or the distance from zero, okay? It's the size of the vector, or here it's the distance from 0 to the point, okay? So if I have the point, or the complex number, 3 plus 2i, and I want to find the magnitude, then that's going to be equal to the square root of 3 squared plus 2 squared, which is equal to the square root of 9 plus 4, which equals the square root of 13. So what's the distance from the origin to 3 plus 2i? It's square root 3. All right, we're going to kind of go over this a little bit later. It's going to play a big role when we talk about complex numbers with regards to trig and parametric functions and stuff. This is a big deal, all right? And it's not too hard. It's kind of simple, I think. But we'll see. Let's move on to some other things that are kind of important to us now. Okay. Boom. All right. How do I add, subtract, and multiply complex numbers? All right. It's easier if we think of complex numbers as a binomial in terms of x, right? Everybody in this room or at home right now should know how to multiply x plus 1 times x plus 2 together. Remember, you used to FOIL when multiplying these together, right? So it's x squared plus 2x plus x plus 2. And then you combine like terms and you get x squared plus 3x plus 2, right? So, oh, wait, did I just add? I sure did. I added these things together. You added like terms, right? So this example talks about how we add like terms and how we multiply them together. So if I have two complex numbers, suppose I have a plus bi, and I want to add that to c plus di, then that is going to equal a plus c plus b plus di. If you don't know how I did that, you should probably come in for some help, because I just grouped them together and factored out the I, all right? And I just told you what I did, so if you don't know what I did, then you have to come back and get some help. So that's for the general case, but let's look at an example. If I have 3 plus 2i, right? That's a one complex number, plus 6 minus 4i, right? What is that going to equal? Well, that's going to equal, let's combine like terms, so it's going to give me 9 minus 2i. What? That's right. Plus 2i minus 4i equals minus 2i. That's it. That's how you add them together. Pretty straightforward. Pretty simple, I think. All right, so let's look at what happens when you subtract them now, okay? So take a minute and pause the video and write this down if you didn't, so that you can have it, because I'm going to erase it now. So now we're going to subtract these two. We have a plus bi minus c plus di. The key here is understanding the distribution of the negative, all right? A lot of people, I've noticed, have forgotten how to distribute. So that's going to be a plus bi minus c minus di, and you combine like terms. So that's going to be a minus c plus b minus di. All right, I hope you see that. Oh, hold on, what happened there? I got an I that doesn't belong. That should have been a, there we go, it's a C. Somehow I made it the wrong thing. I was thinking something else. There we go. Minus D I. So let's look at an example of that. So I have, again, 3 plus 2i minus 4 minus 6i. Right? So I have 4 minus 6i is 1, and 3 plus 2i is the other, and I subtract them, and I get 3 plus 2i minus 4 plus 6i. Combine like terms, I get negative 1 plus 8i. And that's how you subtract them. You just use like terms. All right? So far, so good? I hope so. Boy, do I hope so. Let's talk about multiplication now, all right? All right, so we have a plus bi times c plus di. So if I FOIL this, just like we did on that other example with the two binomials, we get ac plus a di plus bci plus bdi squared. Snap, there's that I squared again, all right? So what's I squared equal to? I squared is negative 1. So now we have AC minus BD. Why was that? That was because I squared is negative 1 plus AD plus BCI. All right, let's look at an example of that. Let's use some numbers now. Okay, so if I have 3 plus 2i times, I don't know, let's go 4 minus 2i. So we FOIL that out, and what do we get? 12 minus 6i plus 8i minus 4i squared. Okay? Let's combine like terms. That's 12 plus 2i minus 4. I'm putting that step in there this time because some people I know are going to, because I know some people are going to mess up on that I squared thing with the negative 4, and they're just going to keep it negative. So two negatives make a positive, so that's 12 plus 4 plus 2i, which is 16 plus 2i, and we have now just multiplied them together. All right? So now we can multiply them, and we can add them, and we can subtract them. All right? Let's keep moving. All right, so now we want to talk about the complex conjugate. I mentioned that a little bit to you before, and it's crazy important, all right? The complex conjugate is crazy important for simplifying things and in solving sometimes, all right? Remember, because when we use the quadratic formula, the roots come in conjugate pairs. All right, so let's talk about this a little bit. If I have the number a plus, where did it go? There we go, bi. And in math, when we want to find the conjugate, we put a line over it. That equals a minus bi. That's the conjugate. So if I have 3 plus 2i and I want to find its conjugate, it's going to be 3 minus 2i. If I have 3 minus 2i, its conjugate is going to be 3, well, let's pick a different example because that's dumb. You can see it already, right? Let's say we have 4 minus 6i, okay? That's a 6. Then the conjugate is going to be 4 plus 6i. Try this one, guys. If I have a minus 2 minus 3i, what do you think the conjugate's going to be? Have you figured out the pattern yet? Minus 2 plus 3i, okay? That's how I find the conjugate. What happens when we multiply these together, though? We're going to take a look at the general case real quick, okay? This is for all of them, right? This will always be what you get, no matter what. All right, so we have a plus bi times a minus bi. Let's multiply these out. So that's a squared minus abi plus abi minus b squared I squared. Oh, you see that? These middle terms, what happens to those? They cancel, they go away, right? So we're left with a squared minus b squared. And what was I squared again? Negative 1. So that leaves us with a squared plus b squared. Whoa. Whoa. That is pretty cool, all right? So if I multiply two conjugates together, I'm always going to get a squared plus b squared. So let's look at one. Let's look at, I don't know, let's pick 3 plus 2i and 3 minus 2i, and let's multiply them together, okay? So we have 3 plus 2i times 3 minus 2i. So that's going to give us 9 minus 6i plus 6i minus 4i squared. The middle terms cancel again, so that's 9 minus 4 times negative 1, which is 9 plus 4, which is 13. Boom. And most importantly, though, the I is gone. Okay? The whole point when we multiply by the conjugate usually is to eliminate the I. Because think back in the day, if you had a radical in the denominator, right? If you had something like 1 over square root of 3, you had to get rid of the radical, right? So how did you do that? By multiplying by root 3 over root 3, right? So if I have an I in the denominator, okay, I want to get rid of, if I have a complex number like 1 over, we'll keep it simple, 3 plus 2i, right? And I want to get rid of the I. That means I have to multiply by the conjugate, which is going to be 3 minus 2i over 3 minus 2i. All right? This is a key skill to have a little bit later on, but I just wanted to introduce it to you and throw it out there to you now. Okay? So we're basically done. I would like you to take a stab at, I'd like you to try these problems, all right? So pause the video, take a minute and try these. I'm going to let the time tick, 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 tock, tick, 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 tock. So you paused it, I hope, and I expect to see these in your notes. All right, guys? Have a good night, and I will see you later.